These two sets of problems represent the same stage of education. On the left, a standard modern elementary worksheet. On the right, a multi-layered equation requiring the student to navigate 3 different types of nested brackets to resolve the expression to 1. Modern arithmetic education often treats early calculation as an end in itself, a series of rote procedures divorced from abstract logic. But the complex expression on the right is not a high school algebra problem. In late 19th century Russia, this was the standard expectation for a student finishing elementary arithmetic. This raises a question of pedagogical preparation. How did a textbook from 1897 train 10-year-olds to parse this without the aid of modern pre-algebra remediation? The answer lies in a curriculum that refused to separate calculation from structure. In the Gymnasium system, arithmetic was taught as the mechanical execution of algebraic logic. To understand the origin of this rigor, we have to look at the educational landscape of late imperial Russia. These are students of the Russian Gymnasium, a system where academic survival demanded total mastery of mathematical fundamentals before a pupil ever entered university. The standard foundational text for this system was Malinin and Burinen's Arithmetic. Surviving 19 editions over 50 years, it shaped the mathematical education of generations of scientists and mathematicians. This text builds student capability through 3 specific phases: the philosophical definition of units, base-independent positional logic, and the treatment of arithmetic operations as algebraic identities. Analyzing this curriculum reveals how axiomatic foundationalism, starting from strict first principles, bridges the gap between simple counting and advanced mathematical thinking. Section 1 of the text bypasses rote counting to define numbers via homogeneous phenomena. It begins by teaching the student to observe the objects and events surrounding them. The authors use the example of a swinging pendulum. Every separate oscillation is a unit. When these identical events repeat, they form an aggregate. The text defines a number as the result of counting these homogeneous units, a collection of things that share the same name. This is contrasted with heterogeneous objects, such as a man and a tree. Because they cannot be given a single name, they cannot be grouped under a single mathematical unit. This logic extends to denominate numbers, such as currency. A gold 5-ruble coin is an aggregate of 5 identical units of value. This philosophical approach forces the student to see numbers as arbitrary placeholders for groups of units, rather than fixed physical quantities. By defining numbers strictly as placeholders for these homogeneous units, the text establishes the structural foundation required to later manipulate abstract variables. The next pedagogical step is decoupling positional logic from the specific digits of base 10. If a student only counts in decimal, they may confuse the base with the underlying logic of place value. In Section 11, the student is forced to translate standard numbers into the quinary, or base 5, system. This diagram shows the process. 2,783 is divided by 5, and the remainder of 3 becomes the first digit on the right. The quotient of 556 is then divided by 5 again. The new remainder of 1 drops into the next magnitude bin, the 5's place, to the left. This recursive process continues until the original value is fully represented by the base 5 number 42113. The text then introduces the duodecimal, or base 12 system, where students must use new letter signs to represent the numbers 10 and 11. Breaking the dependence on base 10 early ensures that the student understands true positional logic. To this student, any arbitrary base, or any polynomial structure, is conceptually identical. Having defined numbers as placeholders, the text systematically redefines arithmetic operations as inverse identities. Subtraction is not taught as taking away. It is presented as the inverse of addition. The equation minuend equals subtrahend plus difference appears here on a perfectly balanced scale, treating each term as an interconnected component. Section 26 explicitly defines subtraction as the act of finding a missing addend when the sum and one other addend are known. The terms shift, but the balance of the equation remains absolute. In Section 35, the authors chart exactly how these components respond to change, building a deep intuition for proportional relationships. If we increase the minuend by 5 units, the difference must also increase by 5 to maintain equilibrium. However, the relationship with the subtrahend is inverse. increasing the subtrahend causes a proportional decrease in the difference. This systematic charting of inputs and outputs directly mirrors the manipulation of variables across an equal sign in formal algebra. By teaching operations as the balancing of mathematical components, the curriculum prepares the student to instinctively manipulate variables as they move into higher mathematics. This structural logic is applied even to complex multi-digit calculations, where the text uses algebraic substitution to bypass the mistakes common in standard borrowing. The authors introduce the arithmetic complement, the difference between a number and the next unit of a higher order, like 100 or 1000. In section 29, subtracting 57,268 from 112,436 is performed through algebraic substitution. The expression expands horizontally, adding and then subtracting 100,000 to maintain the value. By isolating the 100,000 units, the subtraction collapses into the arithmetic complement of 42,732. This transforms a complex subtraction problem into a simple addition. The arithmetic complement demonstrates that mathematical operations are not fixed. They are interchangeable structures within number theory. This background prepares the student for the complex bracketed equation we saw at the start. A student trained in algebraic equivalence parses this expression as a hierarchy of logical instructions, rather than a chaotic string of numbers. They solve the expression from the inside out, resolving the innermost layers and substituting the results until the entire structure resolves to 1. The authors achieved this result through patient development, insisting on concrete motivation for what is genuinely difficult, rather than rushing toward over-formalized modern methods. By insisting on absolute structural logic for the simplest operations, this curriculum produced students who could open an algebra textbook and begin working without remediation. It treated arithmetic not as an end,